Mba633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this segment, we will introduce definitions and some basic concepts associated with design of experiments and analysis of variance. Now, analysis of variance is a set of statistical techniques that tries to understand or determine the sources of variability of some variable. And it's used for different purposes. In this case, where we have just started, we will use analysis of variance to test for the equality of means of multiple populations. It may seem a bit of a contradiction at first, but we'll come back and try to explain that. Why is it that when we're looking to test for the equality of means of multiple populations, why are we talking about variance? So I'll keep that on hold for a few minutes. So let's explain the problem setting here. So we want to examine the calcium content of wheat after different lengths of storage. Now, I think you can easily imagine that the calcium content of stored wheat will depend on a whole host of different factors, not just the length of storage. It could depend on which part of the country the wheat was produced in, what type of seed was used, and so forth. So one can think of many different factors that would affect the calcium content of wheat. In this problem setting, we are interested only in the potential impact of one factor, which is the length of storage. So you could think of the following experiment. We decide that the factor that we're interested in studying is the length of storage. So every experimental design of an experiment will have one or more factors, and the output of interest, in this case the calcium content of wheat, is what's called the response variable. So essentially we are interested in studying, is there any impact of varying this factor on the response variable. So in our case, we have set up 4 different storage lengths, 0 months, 1 month, 2 months, and 3 months, which for brevity I've labeled as M0, M1, M2, and M3. So we have 4 different treatments here. Okay, so the number of levels that the factors can take in the experiment is referred to as the number of treatments. So just in terms of definition for this, the experiment that has been designed here, I'm interested in the impact of a factor on a response variable. In this case, the factor is length of storage and the response variable is calcium content, and I've set up the factor to have 4 levels or 4 treatments. Okay, so I want to see the potential, if there is any impact of the factor on the response variable. One could think of other similarly designed experiments. Your factor could be the dosage of a hypertension drug, and the response variable could be the level of hypertension, systolic or diastolic pressure, and you want to study, is there an impact of different levels of different dosages of a particular medication on hypertension levels, and the level of treatments would be different number of doses in 10 milligrams, 25 milligrams, 50 milligrams, 75 milligrams, and so forth. So with this problem setting, the 2 hypotheses we want to test, the null and the alternate, which is our way of checking if the factor has any potential impact. Look at the way the null hypothesis is stated. Mu M0 equals mu M1 equal to mu M2 equal to mu M3. So in our case, this means that the average calcium level for wheat, which is stored 1 month, average calcium level for wheat stored 0 months, 2 months, and 3 months, they're all the same, they're no different, and I've said it's equal to mu. And notice the alternate, it says not all means are the same. We are not saying that these 4 means are all different from one another. We are saying that at least 2 of them are different. If not all means are the same, then at least 2 have to be different. So that's the null and the alternate hypothesis. So that's what we want to test. So if we are testing the equality of means of multiple populations, by the way, we have already seen how to use the Z and the T test to check for the equality of means of 2 populations. Here we have more than 2, and in particular we have 4 different populations. Wheat that's stored 0 months, 1 month, 2 months, and 3 months, so 4 different populations. So why is it that when we are checking for the means of 4 populations here, why are we talking about variance? The reason we are talking about variance is what you will find first of all, the variance that we're talking about here is the variance of the response variable. By the way, the analysis of variance that I'm about to describe sort of qualitatively for you rests on three important assumptions. One assumption is that the response variable, in this case the calcium content, is normally distributed for each population, in this case for 0 months, 1 month, 2 months, and 3 months. Second, and this is probably the most important one, the variance of the response variable must be the same for each population. So for 0 months, 1 month, 2 months, and 3 months, if you think of those 4 different populations, the variance of the calcium content must be the same for those 4 different populations. Okay, this is what brings us back to and helps us answer the question, why are we looking at variance when we're testing for the means, equality of means of 4 different populations? And the reason is that what ends up happening is that depending on whether or not the null hypothesis is true, what you will find is we will go back and compute this population variance, this sigma squared, which is assumption number 2. We will compute that population variance in 2 different ways. First, we will compute it assuming that the null is true. Second, we will we'll compute sigma squared assuming that the null is not true. Okay, and see how different they are. By now you may recall that the way you test that 2 different variances are equal or roughly equal is that you check if the ratio is close to 1 or not. That's the F test that we had studied some time back. So the way we would check if these 2 different computations lead us to the same result. Now here's the logic. If H0 is true, if the null is true, then whether I compute the population variance sigma squared by the first method or the second method, I should get fairly similar results. The ratio should be close to 1. But if my assumption, if H0 is false, then that ratio would be much bigger than 1. Let's see why that would be the case. Now, if the null is true, then I think you would agree that the calcium level of wheat follows just one distribution, one bell-shaped curve over here that you see, and these 4 different samples that we drew, each of size 6, these 4 different samples are simply 4 samples taken from this same population. There's one population which all 4 of these populations having the same mean. So you would expect these 4 sample means, this 57.49, 57.95 and so forth, you would expect them to be fairly close to one another, and you would have 4 different sample means from which you could get the standard deviation of the sample mean. This would be, and why am I allowed to do that? Simply because the assumption with H0 is that all 4 populations have the same mean. So the 4 samples that I just extracted are 4 samples from the same population. So if I take the standard deviation of 57.49, 57.95, 59.55 and 60.34, that standard deviation would be given by this expression, sigma divided by square root of n. And then because I know n, each sample size is of size 6, I could reverse engineer this sigma. So in this first step, what I would have done is I would have calculated sigma, the population standard deviation, and if I square it, I would get the population variance. I would have computed sigma squared, but it is based on the assumption that the null is true. That is, all 4 populations have the same mean, and hence these 4 samples are drawn from this same population. Now what if H0 is not true? Then the picture looks like what we have at the bottom over here, isn't it? That these 4 samples that we have, the samples M0, M1, M2 and M3, they are drawn from 4 different populations, and their means are different. Now just to make it easier for me to draw the picture, I have drawn mu0, mu1, mu2 and mu3 completely different from one another. That need not be the case. All that needs to happen is 2 of them are different from one another. But I think this picture will suffice to explain what I'm trying to set up here. So if the null is not true, then the 4 populations are drawn from, the 4 samples that I have, M0, M1, M2 and M3, are drawn from 4 different populations. Now remember the assumption number 2, that the variance of the response variable is the same for each population. So each of these 4 bells, even though their means are different, their variances are exactly the same in the population by assumption number 2. If that is the case, then if you go back to the sample, this 1.89, 1.77, 0.80, 2.12, these four sample variances that I got, these are simply approximate values for the population variance sigma squared, isn't it? And that follows based on the assumption number 2, that the variances of these four populations must be the same. So if I average these four values of S squared of the sample variance, if I take the average of 1.89, 1.77, 0.80, 2.12, I would get an approximate value for sigma squared, but this time without having made the assumption that the null is true. So you can see I have come up with two separate estimates of population variance sigma squared, one by assuming that the null is true, one without assuming that the null is true. Okay. Now, if those two calculations if the results of those two calculations are very, very different, then I would know that my assumption of the null hypothesis is false. If those two turn out to be fairly close to one another, then I would conclude that the null is probably true. The rest of the math that we will do in subsequent video clips is to determine quantitatively how different these two calculations for sigma squared have to be in order for me to reject the null. So we have to quantify the uncertainty, but this is basically the logic. Okay, so I assume that the null is true, I assume that the null is not true, and under these two assumptions I calculate the same quantity, namely the population variance sigma squared. If I end up with very different results, then my assumption of the null hypothesis must be false. If I end up with the two values of sigma squared being fairly close to one another, then I know that the null is probably, I cannot reject the null. So this is the reason why we are using an analysis of variance in order to determine whether the means of multiple populations are true. Okay, so in the subsequent slides we'll continue using the same example, but we'll work out the math using the logic that I've just outlined, and hopefully you will see a further insight into why we are using an analysis of variance, and what does the analysis of variance end up doing? How does it identify the source of variability of the calcium content of wheat for different lengths of storage?